And you might want to remind people to mute their mics again.
Yep. So actually, we'll get going here. Is it 7?
Yep.
So everybody, I'm Rick Rolke. I'm serving as the Master of Ceremonies tonight. We'll start with a couple of sort of rules of operation. If you can kill your video and mute your microphones, that will be a big help. We will run, there's a chat function that you can find at the bottom of your screen. If you have any questions, send them to me, and then I will forward those on to Roy. And we are recording tonight's presentation, and the introduction to cross-country recordings came out really great, so this should do as well. Let me figure out how to, there we go. So let's start by introducing your professor tonight, Roy Bourgeois. Roy has been flying in New England since the early days and has logged over 4,000 hours of soaring. More impressively, has logged over 250,000 kilometers of cross-country gliding. Roy does have the advantage of spending his winters, their summers, in South Africa, and gets to rack up a few more miles down there. But that's a very impressive total. He holds all the diamonds and a 750K diploma. He's currently holding 3 US speed records in both open and 15-meter classes, and he holds 6 Massachusetts records. He's competed in 10 United States and Canadian national championships and was on the US team for the 2019 Pan American Championship. Roy flies an ASG 29 here in the States, Romeo Oscar Yankee. And then he has a half of one in South Africa, 133. So let's join Roy now, and I'll turn it over to you, Roy.
Great. Can you hear me okay, Rick?
Yeah, you're fine.
Super. All right. Good evening, everybody. And thanks for coming. And we'll try to make this as interesting and informative for you as I can.
Roy?
Yes?
I forgot my other task here. And that was, as a matter of introduction, a number of our attendees also attended the Intro to Cross Country course. And both Roy and I think it's great that those who are still early in their cross country careers are interested in this presentation. But a word of caution that these are, some of these are advanced techniques. And just like when you're learning to drive a car, it's not that important to hit the apex. So, you know, it's great to learn these things and know what you're looking out for. But as I had said during the cross-country, the Intro to Cross-Country course, it's perfectly okay to make beginner mistakes when you're a beginner. You know, getting high, staying high, not flying as efficiently as Roy is trying to do here is perfectly fine in your early days. Then you can switch over and work on these techniques that you'll see tonight. But some of these things, if executed poorly, will put you on the ground early. And so that's not what you're after for your first cross country. We're looking for maximum success experience. So that's my caveat for tonight's presentation, and I'll leave it at that.
Okay. Again, thank you for that, Rick. And my only caveat is that if all of a sudden the audio goes blank, for a while, it's not you. It means that Roxy, my dog, who's here with me, has started barking because there's something outside that she doesn't like. I do fly gliders in South Africa, and The place that I fly at is a little bit more than just a nice, fun place to fly. It's also a performance camp where intermediate and advanced people come and try to make their game better. And the way we do it is that every day in South Africa, we have a pilots meeting. We have a weather briefing of the type that you'd have at a world championship. And then we set tasks. And we set a particular type of task, an easier one for the newer people and a more ambitious one later. But the type of task that we set is called an assigned task with FAI turn points. And what this means is that everybody is going to fly the exact same task. They are going to turn at the exact same turn points. And the next day, we review all of the flights, and the review is done by a very, very high competency level group of people. In this photo, for example, when we're in the middle of a review of the flight, the fellow on the right-hand side is Jake Bravel. He was the 2018 World Junior Champion. And that's the level of people who were there. And having gone through this, for 15 years and 22 trips, I came to learn some things about my own flying. You'd finish a task sometimes and you'd think you did really great. And then the next day you'd find out that somebody you were flying against, went 10 or 15 miles an hour faster than you did. And it's really kind of humbling. But you have no choice except to find out what it is that that person did differently than you. And invariably, what that person did differently than you was to fly their machine more efficiently. When I first started doing this program, it was called Flying Gliders Faster. But sometimes people felt that that title, going faster, was too oriented towards competition pilot flying and less relevant for the rest of us. But there are reasons why we all want to learn to fly efficiently. And I want to go through just a couple of them here. Certainly in competition, in record flying, and in long distance flying, being efficient is the single most important thing. Gary Ittner, the American racing pilot, once said that competition flying is simply a process to determine who is the most efficient pilot of the group. In addition, if you're interested in OLC, both speed and distance, by flying efficiently, you will increase your OLC scores both for speed and distance. Very often when the day is changing, flying efficiently is going to get you home before the storm or before dark. And it gets the most out of your glider and out of the day. I hope you all did read the John Cochran article where his starting point is maybe you don't need a new glider, you just need to fly yours better and more efficiently. Last and most importantly, I think that flying efficiently is a natural component to our sport. We don't want to waste effort or energy. And really, flying efficiently is all about that. My definition of efficiency means just to not waste time or energy. That usually has the result of increasing your cross-country speed. But what we're trying to do is not necessarily maximize our speed, but maximize the efficiency. So flying efficiently really has very little to do with the actual airspeed that you're going to fly when you're cruising between thermals or cruising on a cloud street. Gliders have a very elegant trade-off, performance and for speed, not unlike a car that the faster it goes, the worse its gas mileage is. And one of the things we'll spend the least amount of time in this program on is on cruising speeds and speed to fly. I think I've got 2 slides on it. Efficiency has a lot more to do with avoiding the things that add time to the task or slow us down. And it has a great amount about your pathway through the air. And in many respects, you could look at the 2 evenings of this program. Tonight, we're going to drill down to a very fine degree on thermaling and climbing efficiently. And tomorrow night, we're going to drill down on efficiency in cruising and where and how to cruise as efficiently as we can. But let's talk a little bit about what are the things that slow us down or add time to the task. And there's a quiz at the end of this. There really is. It's a test. So I'm going to give you a bunch of things here that arguably could slow you down in the glider or are inefficient. The first one is deviating course to get to better conditions. Instead of going straight at your turn point, you may go left or right to get to what appear to be better clouds or a cloud street, but that is also going to slow you down, maybe. Second thing is flying faster than classic speed to fly. Flying slower than classic speed to fly arguably could add time to your task too. Less than optimum thermal selection. Leaving thermals too late. By the way, we're going to talk about all of these things. Circling in sync. Poor thermaling technique. So here comes the quiz. Out of all of these things, which one of the above is the worst? And if you can't pass this test, you ought to take up bowling. Because the easy answer is circling in sync. But look at the bottom line of this screen. We do it all the time. Now, okay, you're probably right now saying, wait a second, Roy, this doesn't make a lot of sense. I mean, you've got us out here on a Wednesday night telling us something we know not to do. But we're going to talk about this in a different way and in a way that you may not realize. I hope all of you are familiar with the CU type flight analysis software. This is an analysis of a flight that I want you to look at with me. And particularly, I want you to look at the pilot's circling performance. He spent 44 minutes exactly circling. He gained 27,585 feet, maybe approximately the height of Mount Everest. But he lost circling 2,000 feet. He circled in sync or in no lift air for 2,000 feet. Now let's look quickly at another flight, if we can. Let's see if we got it here. Yeah, this one here. Another flight. This pilot flew 1 hour and 4 minutes circling, gained 39,455 feet, and lost 4,062 feet. He circled in sync, losing 4,000 feet. Now, maybe these guys are dumb, but maybe they're not. The first flight I just showed you won the Strukov Trophy for the fastest flight in the open class nationals in 2018. The guy went 100 miles an hour, at 101.5, 163.9 kph. The second flight is the current United States 500-kilometer triangle speed record for 15 meter. So if these guys are out there circling in sync for thousands of feet lost, with the efficiency that means, remember, that part of the 39,455 feet, he had to overcome the 4,000 feet that he lost circling in sync. If this is happening to these people, what are we doing at Sterling or your club, you know, on a typical day? So I wanted to take a look at that, and I took at random some flights that were done out of my club. Here's one here where it's a 15-meter glider flown by a competent cross-country pilot, and his total gain was 29,255, but out of that he had to recover a negative 4,760 feet. Now you see up here in the upper right-hand corner, you're seeing percentage signs. This percentage sign is the percentage of this number in relation to this. In other words, it's what I call the thermaling efficiency ratio. We tend to spend a lot of time talking about the percentage of time circling and try to get that number as low, but it's actually not as important a number as the relationship between circling time in sync and total altitude gain. So for example, if you look at this flight here, it's 19%, which is pretty good, but the next flight is 31%, but still this guy is going pretty close to 96 miles an hour, 95 miles an hour. But when we get into the club performance, we start to see here at 16%, and we're up at 39% time total circling. And the next flight is a whopping 26%. This pilot on a cross-country flight flew, had a total climb of 21,535, but out of that amount, 5,700 feet was recovering from the loss of circling. It's as if he was climbing a mountain, and you know, for every 3 steps he took up, he took 1 step down. So this is something that I've become a fanatic about in my own flying, is not so much worrying about the percentage of time circling, because that's a function of a lot of different things. But the relationship between the time circling in sync and the total time circling is what makes the flight efficient or inefficient. It drives this number. And it's not a surprise that when you look at these 4 flights, you see that 19% time, you see the efficiency is more driven by this number than anything else. So now, why are we circling in sync? This is something I'm fond of saying to my students, and that's the thermal is your friend, but it's surrounded by your enemy, and your enemy is sync. And we need to mitigate the effect of this both by 2 things: by thermaling decisions and by thermaling technique. And to understand both and what we need to do differently, we need to study thermals and to study sync so that we know the enemy. You know, if you think about it, nobody has ever done a presentation in your career on sync. You know, we study rising air all the time, but the air goes up and it also returns, and that sync return is just as much of a problem that we have to deal with as anything. So we're going to look now at the structure of thermals with an emphasis a bit on the sync component. Now, some of you remember this photograph from the basic course, and it is it's a stubble fire that shows some important things: the narrowness of the thermal at the bottom, the width at the top, and then part of the basic program was to talk about the sync component, which is coming around and down the sides. It's also important to note that it's roiling or turbulent in this area in two respects. There's a turbulence layer between the still air and the sink, and there's turbulence between the sink and the lift. Okay, somebody's got an open mic. Thank you. So also in the basic course, we looked at these items, and we're going to talk about them in more detail in a minute here, but this is a thermal bubble type, which has the sink coming around it. This is the constant flow type thermal, similar to what we just saw in the photograph. And this is the cross section that we talked about in the basic course. And we used it in the basic course because it's helpful in some respects. It shows that the lift area in the thermal can be off-center, and it usually is off-center, and the thermal is surrounded by sink. But there's a problem with that, and that is just as the lift can be uncentered and offset, so can the sink return. Just thermals frequently don't look like this with an even layer of sink around them. Sometimes the sink return gets deflected. So let's look at another stubble fire photograph. Here what we see is what starts as a basic thermal, but there's so much sink coming down that it's actually creating its own inversion at the side and blowing off. So this is all sink out here, and there's probably stronger sink here. This is a different view of the same fire later on. And what's also interesting is notice this cone which is going up. It disappears behind the thermocloud, and then it comes back up and curls down on this side. Clearly, this is not a situation where we've got a thermal that's surrounded by sink evenly on all sides. And most of the thermals that we encounter in normal flying are not that like that. They have some type of different structure. So just as the lift portion of the thermal is not uniform, the sink return is not uniform. And to add to the complexity, all three of these things are moving, changing, throbbing, and gyrating all the time in the thermal. The strong lift area is moving, it's changing its shape, and it's moving around in this thing, which is the weaker lift area. The weaker lift area is compressing, expanding as the thermal gets higher, and this is moving around in this, and then the sink return is surrounding it and going in the opposite direction. You know, people say, well, you know, in the northern hemisphere, maybe, you know, thermals turn one way, but it's entirely possible the sink is rotating the other way. The point is, sink is extremely difficult to predict, but I find this in some ways a more helpful model than the one that we just looked at. Now let's assume that we're going to try and enter a thermal that looks like this. And our direction here is you know, from the upper right-hand corner, and we make the mistake, because it's easy to make, of starting our turn right here, and we wind up half in and half out. This entire radius here, this long-term travel, which is about half of the circle, we're going to get hammered in this thing. And this is the penalty we pay in this model, you know, for turning too early. Now, we use the same model for an exercise turning too late. And again, out here, at least we're in still air, and all we have is the sink component from the glider's turning polar. But still, this is going to add to our time of circling in sink. The ideal is this, which is to start our turn perfectly and center directly here. Now, this requires a tremendous amount of practice. People ask me, you know, what can I do to practice to become a better pilot, a better cross-country pilot, a record pilot, a competitive pilot? The answer is what you should practice more than anything else is thermal entry efficiency. Around the airfield, find a thermal, practice coring it quickly and perfectly with no point on the variometer where you're not climbing. If you look at this thing, if you listen to nothing else from tonight's presentation, read this. The efficiency in doing thermal entries with no time in sync or no time in still air is the single most important thing you can accomplish. When you're at the airfield and you see these people, like Doug Jacobs and some of the other world champions, and you're trying to figure out, what do they do that's different than me? This is what they do that's different from the rest of us. And that is they pull into these thermals, they find the core immediately, and once they find the core, they rack it up. Let's look for a second now at the advantage of the same sequence we just went through, but now we're going to circle a little bit tighter. The early turn, if the pilot makes it tighter, notice the radius that he's out here getting hammered in the sink is much smaller. His time out there circling in sync is much shorter. When in doubt, when you think you're in lift, rack the glider over. Now, there might be a couple of you sitting there saying, well, wait a second, Roy, what about the turning polar of the glider? I saw this article, about turning rates and British standard thermals, and it said that, you can calculate the perfect, the optimum circling bank by the glider's polar. To which I say, hogwash, bunk, forget it. We don't care about the glider's turning polar. What we care about is getting the heck out of this sink. Why do we speed up in sync? We learned that at the very beginning. We speed up in sync because we want to spend less time in it, and the hell with the fact that our polar, as we speed up, is getting worse. We want to spend less time in sync. So same thing now for our late entry into the thermal. Once again, you can see that there's a benefit, less time spent in the still air. You get quicker to the transition point where you can figure out what's going on. That the transition point is where your variometers start to rise, and to start penetrating into this area because this is what's making the varios rise. You get there quicker. And once again, for our pilot that centered the thermal perfectly, the tight circle gives him or her more time in the strongest area of lift. Steep turns and steep entry turns, once you know that you're getting into the good area of lift, are fundamental. And when I mean steep turns, I mean steep turns. If you are not turning steeper than you think you should, you're probably not turning enough. One thing Doug Jacobs used to teach the juniors was to practice 15-second turns. Now, in John Cochran's article, he talks about the typical experienced glider pilot circling at about 25 seconds to a turn, which is a pretty steep turn. 15 seconds has the glider pretty much right on its ear. But as we've seen in these three examples, circling steeper helps in every situation. Even if you make a mistake, you're likely to spend less time in the mistake area. Now, I want to make two more points before I leave this model. And this is an important thing that I think beginning and even intermediate pilots don't always understand. When you fly a glider at a tangent to the sink area, it behaves exactly as if you're at a tangent to a thermal. what's going to happen with this glider? Number one, it's going to hit the turbulence that's associated with the boundary layer between the sink and the undisturbed air, that roiling that we saw in the vertical models. And that's going to make your Vario bounce and chirp and do all kinds of things. At the same time, the right wing is going to go down, the left wing is going to go up, and it's going to give you the exact signals of a thermal over here. And if you get suckered into this, you wind up doing one of these. There's no thermal there. Oh, now it's time for my 270-degree correction. And we go down into this crap. And you just get hammered. So we're going to need to find a way to deal with this, and we're going to talk in a minute about it. But it's always important to ask yourself, what am I seeing here? What made that wing go up? Well, the answer is, in this situation, it was the sink that made the other wing go down. But this is something we're going to tell you how to deal with in a minute or two. The second thing I want you to look at is the implications of this kind of model for so-called dolphin-style flying. Dolphin-style flying is when you pull up and slow the glider dramatically in the thermal and fly slow and go straight across. Well, okay, so our glider here is going, let's say, it's cruising at 70 knots and pulls up here to 45 knots. And you're enjoying the fact that you're climbing, but then you get out here, and now you're 45 knots, and you're getting hammered in the sink. You're slow in the sink, and you lose, by being slow in the sink, everything that you gained here. We're going to talk a little more about this later on. But slowing up in lift means that you're going to be slow going across the sink that surrounds it, and it's usually a waste of time, and sometimes it's a net negative. Okay. So what we got to do is we've got to change our techniques, and we're also going to have to change our thinking. So let's talk first about techniques. We've already seen the need and the benefit of perfect entry turn timing and tighter entry turns. That's what we got to practice. That's what we're going to get good at. Every thermal we want to do perfectly. We never want to see that variometer needle dip or duck down. It should be a constant rise right in, and then we're thermaling steeply and going up. We've also seen here, I hope, the benefit of Cochrane's suggestion that thermals should be selected based on how easy they're going to be to center, and not necessarily on the initial vario pulse. This idea of Cochrane's helped me immensely. It was a big change in my flying, and I still do it. I come into a thermal, and if the glider is surging all around me, the wings are flexing, I'm pressing down in the seat, and I know I'm right in the middle of it, fine, that's going to be an easy thermal to center. But if I'm getting bounced around and the vario is scooting all around from one stop to another, that's not going to be a thermal that's easy to center, and I'm not going to chase it. Third thing, and this is most important, we need a technique to really quickly recognize when a turn is a mistake before we commit to it. Because we don't want to spend our time circling in sync. Now, I call that the 60-degree rejection approach. I'm going to get my highlighter here ready. Okay, good. Now, what's 60-degree rejection? We do not commit to a full turn into the thermal. Instead, when we feel like, okay, there's a thermal here, it's time to start a turn into it, we're going to commit only to turning 60 degrees into that turn. And at the 60-degree point, around the first turn, that's when we're going to make the go, no go decision. That's when we're going to commit to a full go around, or whether we're going to bail out and keep going. During that 60-degree turn, we get hyper alert, and we're looking at everything. First, and most important, even more important than the vario, is as I turn into the thermal, during that first 60 degrees phase, is the glider loading up? And by loading up, I mean, can I feel the wings flexing? There's 3/4 of a ton of mass that I'm strapped to, and it creaks and groans and stretches when it starts to lift. And I want to feel if that's happening. Am I starting to feel pressure in my butt? That I'm starting to get pulled up with the machine. And is the vario following? Is the thermal working? Or, and if it is at 60 degrees, then I'm going to roll that thing right on its ear. I'm going to rack that machine over, and I'm going to go into that steep turn we talked about. But if it's 60 degrees, something's missing. The surge or the pressure is gone, or it never happened, or the vario is starting to tuck now. It's starting to go to move down into the low range and almost down to zero. Then I'm going to cut off that turn at 60 degrees. I'm going to roll the glider back on course, and I'm going to keep going, and I'm not going to look back, because there's going to be other thermals, but I'm not going to fool around with that one. So it looks kind of like this. This is our thermal, and we're coming on this way, and something happens, but we're a little late, and we start the turn down, and nothing's there, so I'm gone. I just keep going. Similarly, coming up this way. "60 degrees, and I'm gone." And I do this in all of my flying. I think everybody does. Everybody who's really studied this recognizes that the most important decisions you make are the thermals you reject, because the thermals that you reject are the ones that are going to take your time, they're going to kill your efficiency, and you're going to wind up spending time circling in sync or in nothingness. And this strategy is important. It takes a mind set change, because in the beginning, we're suckers for thermals. And we start, and they tease us, and we wind up spending all kinds of time fooling around with them. And there are 20 other good ones out there. So we've got to learn to change our decision making a little bit. Roxy. Rick, is this a good time for questions? Rick, are you there?
Yeah, I am. I don't have any questions from the audience, but I have one from me.
Okay, go ahead.
Would you generalize that the sink is more on the downwind side of clouds, or is it truly randomly distributed?
As best as I can tell, I think it's randomly distributed, and
Okay.
it changes with altitude. I actually think that the sink twists around the thermal stalk sometimes so that it may be bunched on the upwind side at one point at altitude, and another point it may be on the other side. So
I have one more question from the audience.
go ahead.
That is, do you stop and inspect most thermals with the 60-degree extent, or do you have another criteria that says I'm not even bothering at 60 degrees?
Now, the 60 degree is something that I use when I've made the decision that I'm going to, okay, this is a thermal I'm going to, I'm likely to want to use. In other words, there's a big fat cloud there. There's something going on that I like. Maybe I see a bird circling. I see a trash bag up there in the sky or something like that. And so, and I'm always flying in areas that I think there's going to be lift. That's going to be what we talk about tomorrow night. But what I don't do is I don't commit to one turn in a thermal. That's a huge mistake, and it's incredibly inefficient. Because if you commit to a turn every time and you're wrong, you're going to lose hundreds of feet and at least a half a minute. Remember, Cochrane's whole goal of his article was to save you 3 turns in a task. And he said 3 turns in a task was like a new glider. So why should we be taking turns willy-nilly? I only go beyond 60 degrees when I know that that's going to be there. Okay.
And lastly, on this topic, it has a question about the high, medium, and low bands, and that I'm assuming we're talking about this at high and medium and not at low.
We're going to talk a little bit about that, but the answer is at high and at medium, I am still flying this way. It's a false economy to think, all right, I'm in the middle band now, so I'm going to fool around circling in sync and find that damn thermal. If the sky is working, the sky is working. If the air is alive, the air is alive. There will be other thermals. And we get nowhere by turning around and chasing after a thermal that, as we already realized, might well be the tangent between sync and still air. So we're going to change our whole approach to thermaling. Let's look at this is what I mean when I say we're going to change our decisions. We're going to select thermals based on how easy they are to center. We are not going to use thermals at the top of our height band, no matter how strong they are. And in fact, we're not even going to slow down for them. Now, how many times have you guys and gals, climbed up to cloud base and you're within, 600 or 700 feet of cloud base, and then, you do everything right and you exit, and 30 seconds later, you hit a boomer. And this one's even stronger than the one you just left. And do you slow down, roll in, and do it? You're crazy if you do, because the most you're going to get out of it is 600 or 700 feet, and you have a significant risk that you're going to make a mistake and wind up in sync. So what happens, and we'll talk about this in a minute, is we're going to make a risk-benefit analysis for every thermal we come into. How sure am I that I can easily center it and climb? How much of a benefit will it be to me if I can? And if the risk-benefit analysis is, nah, don't do it, we're not even going to slow down for it. And the last point, we're going to pass on any thermal that doesn't feel right at 60 degrees. There are going to be other thermals there. And if a thermal gives us trouble, we're going to leave it. You know, if we're getting bounced around, if we can't center it, it's not going to get better. Leave it, go on and find a better one. There are scores of thermals in that sky. We've got to change our thinking. We tend to think of thermals like a life preserver and we're drowning and we're going to grab onto it no matter what. That way is inefficient. That's that thinking is the cause of inefficiency. Thermal is just a foothold as we're climbing the mountain, and we're going to use it while we need it, and then we're going to move on to the next one. And anytime a thermal starts to weaken, we're going to leave it. We're going to leave by passing across the lift area, gaining speed. We'll talk about this more in a minute. And we are always going to know the exit direction and pass along the lift in that direction. How many people, we can't even have raised hands here because we're doing this online, have been in the situation where you get so wrapped up in the thermal, now we get close to the cloud base and it's like, okay, which way do I go? Which way was my course? You know, your compass is spinning like a top, and you can't really see much except straight down at the ground. The big cloud you wanted to aim at, you can't see anymore. So there's a trick to doing this, and we're going to talk about that in a second. Lastly, we never go back to look for a thermal we lost. Never, ever, even when we're low. Now, if we're frightfully low, we're down at the bottom of our height band, we're in survival mode, we're not going to leave zero sync. We're not going to leave a thermal. But if we've lost it, we're going to go find another one. We're not going to go back and look for that one, because 9 times out of 10, the reason you lost it is it was a bubble and now you're below it. Okay. Leave by passing across the lift area, gaining speed. Now, one caveat about this trick. You do not do it if there are other gliders in the thermal with you. But basically what you do is you're thermaling and thermaling and thermaling, and my exit direction is this way, and my track direction is this way. What I'm going to do is, as I'm getting up to cloud base, I'm beginning to move a little bit towards this, and now what I'm doing is starting to speed up. I'm going for speed now. My flaps have come out of climb mode. I'm back into cruising mode. I'm speeding up, I'm speeding up, I'm speeding up. And I'm using the energy, rather than get sucked up into the cloud, if I'm close to cloud base, I'm converting that energy of the thermal to speed. I turn now and I come wailing out here at my normal cruising speed. Instead of doing this and crossing the sink slow. So basically you cut across the lift area, gaining speed and punching out that way. And frequently you can do this, by the way, and pull up, do a pull up here and find yourself, 300, 400, 500 feet sometimes above cloud base. Rick Rolke will explain to you also that when the wind is coming, this is an easy way to do the thermal to wave transition, but that's not what we're here to talk about. So this is what I mean by circle across the lift and leave. We do not do it with other gliders. It would be dangerous to do it with other gliders. We're going to always know the exit direction because we're going to target ground features and head for them. This stupid little drawing took me an hour to make, okay? But it illustrates the problem, and that is that as we're circling up here, in a thermal under this cloud, once we get here, we can't see the next cloud that we want to go to. All we can see are features that are on the ground. So if I'm thermaling up here, and as I get to about here, I realize, okay, I'm going to lose definition on this cloud that I want to go to. This is going to be my next cloud, and that's going to be my next cloud. So what I do is I look at a ground feature that's under that cloud. Oh, okay, there's a little building here. Because even when I'm close to the cloud base, I can still see the ground features, but I can't see this cloud. You know how the very best clouds get bowed like this? They have a concave underside. And particularly when you get up in that concave area, you can't see anything except down. So what you're doing is as you're climbing, as you get into the mid-level of where you're climbing, you know what your exit direction is going to be. You're selecting your next cloud, your next area. And we're going to talk more about this tomorrow night. You pick your next place to go, but you mark it by means of something on the ground because that's all you're going to be able to see. And then you go right up here. You do what we talked about before. You go to the back. You come pick up speed, go wailing out, and you're aiming at that ground point. And it's a very effective way of doing it. If you don't do it, you can get easily confused. And if you come up the wrong direction, then you're going to spend more time circling in sync, or at least circling in still air. More about changing our thinking. We're still oriented to the idea of get high and stay high. But tomorrow night in this course, we're going to talk about our pathway, about how to reduce the sink by your pathway. And we're going to focus on different, better ways to do it than taking every thermal or taking thermals that we don't need. This part's important. Every decision to thermal is going to be done with a risk-benefit calculation in mind. What's the risk that this thermal will slow us down? What's the benefit of taking a climb here? Is there a way to mitigate the risk of taking a climb here? Do I really need this climb? What's up ahead? Do the clouds look better up ahead than this particular one? What's outside? Birds or other gliders, etc. Simply put, we're ending this, this desperation, I'm going to latch onto every thermal kind of thinking that we grew up with and that we began our cross country with. We've got to change the way that we think and the way we think about thermals, and we've got to be picky about them and decide, do we really need it? Going back to the point we made the other night, a few minutes ago, if you're leaving a thermal, 700 feet or 600 feet below cloud base and you hit a boomer, what's the risk-benefit calculation? The benefit is 600 more feet. But the risk is that boomer is going to have horrific sink around it. Remember, that air's got to go down too somewhere. And if you make a mistake, you're going to get clobbered for no good reason. Every thermal is like this. Every thermal is a risk-benefit calculation, and you think long and hard about stopping to thermal. There was a famous racing pilot who once said, in a casual conversation I was involved in, he said, I view the decision to thermal as a surrender. In other words, what he wanted to do was to keep cruising all the time, and the thermal was when he had to. And then when he had to, he wanted to make sure he did it perfectly. That's what gets us to the last thing, which is the optimum pathway through the air. But that's going to be something we talk about later in the program. So thermals, use the best and leave the rest. Study the strength of the thermal as you climb and know what the good height band is. Now, what am I talking about here? One of the benefits of learning how to properly center a thermal and staying in that center all the time is you get to realize that as you're climbing, the thermal strength changes. And it changes because the air mass that the thermal is climbing through has a temperature profile that's uneven. we're going to look at this in more detail in a couple of minutes. So if we're flying along, and let's say let's take a typical day at Sterling, and we get off tow at 2,000 or 2,500 feet, and we start to climb, and we're climbing at 2 knots, and all of a sudden at 4,000 feet, the 2-knot climb becomes a 3.5 or 4-knot climb. And it stays like that until about 6,000 feet and get closer to the cloud, and then we drop off. Well, we just learned something. We learned that the thermal got better at 4,000 feet, and it began to drop off close to 6,000 feet. That's a healthy height band, and that's what I mean by the good height band. It's something different than the height band concept we talked about in beginning and basic cross country. But each day has an optimum thermal strength height band that we need to learn. And we find the speed or the rhythm that keeps us in that good band, and try to not go below it if it's at all possible. It's almost always better to leave the thermal early than late. If the thermal is still climbing, if it's still solid, there's not really a lot of penalty in leaving it early. You will find another one. There'll be another one that's out there like that. I have a funny story that's an illustration of this. The very best day I ever had in competitive soaring, I brag about it, if I can brag for 1 second, I beat the Concordia that day with an 18-meter glider, and I beat the Concordia. And the reason I beat the Concordia and almost everybody else was that I didn't have oxygen. I forgot to pack the oxygen. And the thermals were going to 15, 16,000 feet. But I wasn't. I was cutting off the climbs at 12, 12.5, and just banging out there. And what happened was, of course, the piece of thermals that I was consistently using was better than the aggregate pieces of thermal that everybody else was using. And I was just that much faster. So there really is very little penalty to leaving the thermal early. Lastly, and this is important, when you're doing a task and you've been far away from home, there's a tremendous temptation to milk a thermal to force the final glide. You've been hitting 5, 6, 7 knot thermals all day. But the thermals are beginning to taper off at 5,500 feet. So all of a sudden you realize, hey, wait a second, if I can just get another 1,000 feet, I can get to 6,500 feet, even in the weak lift, I've got final glide. That is a big mistake. It's inefficient. You spend too much time trying to milk out that last 1,000 feet. And more importantly, what's going to happen in that final glide is you're going to fly through 4 great thermals, tremendous thermals, and you can't use them because you're on final glide. So let the final glide come to you naturally. Just keep doing what you've been doing, and all of a sudden, hey, I'm on final glide, and bring the machine home. Lastly, as I said, change the acceptable range for thermals as you get lower. We're still not going to fool around with difficult to center thermals when we're low, but the acceptable range of thermals, as we get into the bottom of our height band, obviously we get into the beggars can't be choosers department, but you got to be tough as nails when you're up at the top. Okay, let me go through this, and we've been going for about an hour, and I've kind of a stop point, but I want to go through this and then we'll take some questions for a while. This is an XY table, which is going to help us talk a little bit about thermals. So this is altitude, 1,000 up to 6,000 feet. And this is thermal strength, 1 knot, 2 knot, 3, 4, 5, etc. Now, there's a myth, and it is a myth, that thermal strength is linear. And we think that a 4 knot thermal, on a 4 knot day, the 4 knot thermal leaves the Earth at 4 knots and it continues up at 4 knots. And it stays at 4 knots until it gets to 6,000 feet of cloud base. But that's not what really happens. Remember that the speed of the thermal is a function of the temperature difference between the thermal and its surrounding air. As the temperature difference gets greater, the thermal grows faster and stronger. We read SKU-T charts and we think that the temperature drop-off is linear, but it's not. What actually happens is we have some inversion and residual inversion from the day down in here, and we have tongues of pretty cool air up here. So the growth of the thermal actually looks a lot more like this, whereas at 1,000 feet, the thermal strength is, so-so. It wanders up here to 4 once, and then it starts to pick up a little bit, and then it hits a band of cold air, and it really pops out. And then up here, it begins to drop off, and the cloud base is up here somewhere. There's a lot of important things that come from this sketch. Number one, this explains why you shift gears in the kind of thermal that you're going to use when you get low. I mean, it's great to have these 5.5 knot thermals up here, right? But the bad news is when you're at 1,500 feet or 2,000 feet, they don't exist. And it's the same thermal, it's just that it grows in strength as it gets higher. The second thing that's important to recognize is that you can learn this. You learn it by measuring every thermal that you climb in. And you're tracking how's your climb going. And you're adding to your knowledge base about the day and about how thermals are going to grow this day and where is the good band. As the day wears on and the heating in the fetch area increases, the thermal strength increases, but even when it increases, it looks like this. The shape of this XY table will stay the same because there's a tongue of cold air here that's making this thermal really rise at this strength, +7. There's residual inversion down here that's making it kind of poke around. So once we learn this, it's extremely valuable. Now, a few minutes ago, I talked about stay in the optimum height band. Well, this is your optimum height band on this particular day. And that is, the best thermal climbs are between, in this graph, 3,800 feet and 5,800 feet. And this is where you want to be. This is the sweet spot for the day. This is where you're going to get really good climbs and you want to keep going and, stay in this area. All right, so we've gone about an hour and 5 minutes, Rick, and this is a good stopping point. It's about halfway through the presentation, and we've covered a lot of stuff, so maybe we should stop and take some questions. But let me explain that tomorrow night's session is going to be an awful lot, not so much about thermaling, but about pathways through the air, finding energy lines, more than just cloud streets, but energy lines, connecting pathways, when to divert, when not to divert. and how to change the L over D of your glider from what it is to twice what it can be if you're going in air that's even going up a little bit. So, Rick, let me stop here and we can maybe field some questions.
Sure. I've got one that came a little earlier, which was how often do you skip thermals and just fly straight through? Do you have sort of a percentage of thermal attempts?
Yeah, well, let me answer that the way I answered it before. Every thermal is a risk-benefit analysis. There is always a risk of circling in sync. There is always the reality that I'm not progressing towards my goal anymore. I'm turning away, I'm standing still. And so I go through a risk-benefit analysis. Do I need this thermal? Do I think it's a good thermal? Is there a bird out there circling that thinks it's a good thermal? Is there a racing pilot that really knows what they're doing in that thermal? How high am I? How close to the cloud base? How much am I going to climb? Am I at a comfortable point in my height band? Do I need it? What's out ahead of me? You know, is there a big fat building cloud that every time I look at it, it keeps getting bigger and bigger? These are all the questions that I'm analyzing every time I'm thinking about thermal. And so the answer is, how often do I thermal versus how often do I pass them up? It's the result of that risk-benefit analysis that I'm doing every time I'm thinking about it. So if I'm up at the top of my height band, it's got to be the greatest thermal ever made for me to for me to slow down and take the risk of circling in sync. But if I'm getting towards the lower part of the height band, then I'm not so choosy anymore. I'm going to come out of the program and go back to camera a little bit, if I can do that. And I'm going to stop sharing. All right. Well, you know, somehow along the line, we picked up more participants, so that's good. Any other questions?
We have one that asked about the performance of the gliders in terms of this general strategy. You know, if you have a low performance glider, do you fly the same strategy? I actually had replied to it to say the fundamental strategy stays the same. You just don't have as many choices. But feel free to contradict me if you feel differently.
I think we do. The answer is most of the strategy stays the same. And in some respects, some of this is more important. The idea of that optimum lift band and not going below that optimum lift band is frankly more important than in a 126, probably than it is in a modern 18-meter racing glider, because you've got the 126. You can't make as many mistakes. You know, you can't explore different ideas. You can't, you know, you can't flop out of two clouds in a row in a 126 because you're going to be on the ground. So in some respects, not only do you follow it, but I think it's more important the lower performance the machine is. That's my sense.
All right, we have a new one that just came in here. Let's see. Yep. Coming in fast and furious. On some days, the thermals weaken, but then strengthen again as you get up to cloud base. How often do you take thermals all the way to cloud base?
Okay, well, look, there's two questions there. There are weak thermals and strong thermals on a day. But it's also important to know why this thermal is weak. If you remember the chart that we just looked at, all right, if you're below 3,000 feet or 4,000 feet on a day with that temperature profile in the air mass, all the thermals below 3,500 feet are going to be weak. And it's simply because that's the way the profile works. So meanwhile, sometimes depending on the thermal source and what I call the fetch area. The fetch area is the area that the warm air has been drawn from. Some thermals start out a lot stronger. For example, in a rock quarry, at midday, we have a lot of rock quarries near where we fly, and the sun beats on the side of the rock quarry at almost a perpendicular level very early. And then the air starts to come up that rock wall, and it continues to heat as it's coming up before it separates. And so those thermals are going to be really warm, and they're going to be really strong and different than the other ones. So first question is always, why is this thermal weaker? Because you don't want to leave a thermal of 3,500 feet on a day that it's going to blossom into a great thermal at 4,500 feet. And that happens. How often do I take cloud thermals up to cloud base? Was the other part of the question, and the answer is never, unless I feel like I need to. And a time of needing to is if I have to cross a blue area, then I'm going to get the glider just as high as I can before I go out into the blue area. If I have to cross an overcast area, and we're going to talk about this tomorrow night, crossing blue areas, crossing overcast areas. But if I'm going to go over an overcast area where I'm not sure if that overcast area is going to be left there, I want to go into it high also. Now, if a thermal is staying really, really strong as we get close to cloud base, and we've got one of those dome type clouds, which is cupped on the, that's like a dome underneath, and its cloud base is higher than the other ones. Those ones I'll pretty much take until the lights start to go out. And what happens is when it starts to get a little dark and you're getting close to the cloud, that's when I go for speed. And I open the turn up, I go to the far end, and I come shooting across as fast as I can on the direction of travel. So I'm using that strong lift for speed to punch out of the thermal.
All right, we have another, although this may be more appropriate for tomorrow's presentation, but if your course line is more or less upwind, how often do you leave the thermal directly upwind thinking you will fly in lift street?
And we will talk about this tomorrow night. Flying, the answer is it depends a lot. In New England, we get frequently I don't call it a wave pattern, I call it an oscillation pattern, where you have waves that are peaking about every 6 or 7 or even 10 miles, and they're tripped by the high ground that's out to the west. So a lot of times, you may have noticed if you're flying upwind out of our home airfield, you'll go through a long dry spot, and then all of a sudden you hit a spot where there's lift everywhere, and then you go through a drought area again, and then another area. That's that oscillation thing. So I'm always trying to find out what's happening as I'm going upwind. Is it that kind of a day? Is there cloud streeting? that I can use. If there's not cloud streeting, are there energy lines that I can knit together by going from one thermal to another to another? So it's not so much a function of how high do I take the thermal, with one exception. You should be really busy in the thermal. Remember, you're trying to figure out where you're going to go. You're going to figure out your next thermal. You're going to monitor the growth rate. But another thing you want to monitor is the wind. If you're going upwind and the wind at cloud base is 25 knots and the wind 2,000 feet below cloud base is 15 knots, do you see how it's kind of crazy to go up to cloud base? You're just going to get hammered with that 25 knot nose on wind on the nose of the glider. So before you decide your upwind strategy, I want to understand a little bit more about the wind speed profile as we're getting higher. So that helps me decide whether I want to get high or not. Some of you are power pilots, and you know, I used to fly a J3 Cub, and you learned to handle the wind. You know, when you're going downwind, you got as high as you could because you got the benefit of the tailwind. When you're going upwind in the Cub, you wanted to be down low at 500 feet because you didn't want to fight that, and the wind gradient helped a lot. So upwind, you've got to get a lot more information before you decide what you're going to do.
All right, and the last question we've got here was, if you'd remembered your O2 on that day that you beat the Concordia, would you have had the discipline to stay below?
Answer, probably not. Probably. You know, that was, I tell that because it's a funny story. I won by screwing up, you know, but also if you go back to the chart that I saw, it's the chart that we looked at. You know, when lift drops off as you get higher, it's helpful to leave it because your average rate of climb for your flight is going to be more efficient. So I got lucky with a screw up on that one.
It's a good story.
Anything else?
No, I think that's it. I think we're all set for this evening.
Well, I hope you've, I guess we've got 35 participants, so that's wonderful. And tomorrow night, just so you understand, there will be a new Zoom link. I don't know how to continue a meeting to another day, and you don't want me to experiment. So probably later tonight, and again tomorrow, you'll get the Zoom login data and password that we needed. Rick, did you need a password for this?
For me, when I click on those links, it has not asked me for one.
Okay, all right. Okay, so
I don't know if that's universally true.
So there will be additional stuff, and some of the stuff tomorrow night is going to be fun. You know, we've got some really fascinating cloud pictures, and you know, most of our session tomorrow night is going to be on cruising and things like that. Okay.
All right. Just before we go, I think there's another question here that looks like there was possibly some confusion. It says, you suggested aim for 15-second circles. You also suggested 60-degree arcs to make initial decisions accepting your thermal. Do you make your 60-degree decision-making arcs as if you were entering a persistent 15-second circle or a more shallow bank?
A more shallow bank.
Yeah.
What I said was only when I am satisfied that the 60-degree turn And remember, I'm not talking about a turn with 60 degrees angle of bank. I'm talking about a turn 60 degrees from my direction of travel. And that starts as usually a fairly moderate bank turn, but only when I make the decision to commit to the thermal do I really rack it over. And that's when, I've got the glider pretty much on its ear and the stick is coming back and the nose is on the horizon. And but that's when all signals are go. And it happens. The question nobody asked was, how many thermals do I reject for thermals that I take? So I'll ask that question. And the answer is I reject about 4 for every one that I take.
Very good.
That
That question was asked actually, but I think it was misunderstood. So that's great. Okay,
so the answer is I do the 60-degree rejection about 4 times for every thermal that I commit to. And I do make mistakes. I mean, I'll commit to one, I get sucked in too. So, but I hope you found some of this helpful, and I hope you find tomorrow night helpful.
All right. Okay. Well, thanks everybody for joining us, and we'll wrap it up.
All right. And Rick, stay on for a minute if you could.
Oh, okay. Then let me figure out how to